Alright, in this video we're going to look at some examples of how to apply the ratio test, which we introduced in the last video. Okay, so here's a reminder of what the ratio test says, and I will show you how we tend to use it. Okay, so here we have an infinite series, and we want to analyze it to determine whether it converges or diverges. And we're always going to start these problems, if we use the ratio test, by taking the limit of the n plus first term divided by the nth term in absolute values. So what does this look like? Well, this is a limit as n goes to infinity. Now the n plus first term would be 3 to the n plus 1 divided by n plus 1 factorial. Now if I divide by the nth term, in order to save on writing, rather than write it as division, I'm going to immediately write it as the multiplication. So when you divide by the nth term, you basically multiply by its reciprocal, so it'll become this. So hopefully that doesn't confuse you. I'm trying to save on writing because it can be so many expressions that you don't want to be writing all over the place. Okay, so now we take note of things that cancel. So I've got n plus 1 3's up here, I've got n here, which means I can cancel out, and that leaves a 3 behind. And n plus 1 factorial would mean, so there's just this one time I'm going to show you that that's, n plus 1 times n minus 1 all the way down to 1, and this is n times n minus 1 times n minus 2 all the way down to 1. So these clearly cancel, and I'm left with an n plus 1 down below. So after all is said and done, I've got the limit as n goes to infinity of 3 over n plus 1. And we can see that that goes to 0. Now we apply the criterion of the ratio test. 0 is less than 1, and that means that our series converges by the ratio test. All right, the r values that you have to multiply to get from term to term become arbitrarily small and approach 0. So it's like a geometric series, but the r value just keeps getting smaller and smaller. So clearly it's going to converge. Let's do another example. Okay, to analyze this one, we again start the same way. We take the absolute value of the n plus first term, and then divide by the nth term. Okay, so with some cleaning up here, by the way, note that this becomes n plus 5 factorial here. I'm going to leave behind a 5 here, and the 5 to the n will cancel. N plus 5 factorial divided by n plus 4 factorial will cancel everything except an n plus 5. So this becomes the limit as n goes to infinity of n plus 5 over 5. Now as n goes to infinity, this goes to infinity. And infinity is clearly bigger than 1, so that means that that diverges by the ratio test. Okay, it's telling us something about the behavior of these terms. It's basically telling you that as you go out, to get to the next term, you're going to have to be multiplying by a bigger and bigger number, and that common ratio, I mean, that's not the right term, but that ratio just grows without bound. So clearly, if the terms are getting bigger and bigger in that way, they have no shot of summing up to something. Let's do one more example. Okay, so again, we start by taking the limit as n goes to infinity of the absolute value of the n plus first term and then divide that by the nth term. Now, to get a handle on this, we don't really want to multiply anything out. What we want to understand is, first I'm going to write it as one fraction. So this is 6 plus n plus 1 squared all times n squared minus 1 divided by n plus 1 squared minus 1 times 6 plus n squared. And then again an absolute value. Let's do some anticipating here so that we don't have to do more work than we need to. If I imagine multiplying the numerator out, in that left term I'm going to do n plus 1 squared. That's going to give me an n squared plus some stuff. And then I'm going to multiply that by the right term, which has an n squared. That's going to be n to the fourth plus a bunch of terms that have smaller powers. So this is going to behave like n to the fourth in the numerator. And if you look at the denominator, I think the same thing will happen. So n plus 1 squared in the left gives you n squared plus stuff. And then on the right term, you get 6 plus n squared. And when those terms multiply, you get n to the fourth plus stuff, right? So I can actually say that this limit equals n to the fourth over n to the fourth. I'm not saying that the expression equals n to the fourth over n to the fourth, but the limit of that expression and the limit of n to the fourth over n to the fourth is the same. So this is clearly the limit as n goes to infinity of 1, which is 1. And here's a situation where you used the wrong test. So we'll see that there are other tests we can use for a problem like this. But this means that the ratio test is inconclusive, and we don't know yet if this converges or diverges. So you chose the wrong test if you use this one. I'm just going to finish with a little comment. The ratio test is great to use for problems that have exponential terms, like 5 to the n, 6 to the n, etc., and or factorials. Okay, the ratio test is, those problems should pop out as ripe for ratio test type problems. Here, this one had neither, and in this case, it was not the right test to use. Okay, so that's the ratio test and some examples.